the substitution method, or U substitution, for indefinite integrals. In general, integration is considered to be more difficult than differentiation because there are no set rules for evaluating integrals equivalent to the product rule, the quotient rule, or the chain rule for evaluating derivatives. And that brings us to the method of substitution. So one of the most common methods of integration is called the substitution method, or U substitution. And we can think about it as the chain rule in reverse, or the method for undoing the chain rule. So the chain rule, if you remember, says the derivative with respect to x of a composition f of g of x is equal to f prime of g of x times g prime of x. So what we want to start to think about is that in the integrand, we are going to have the result of the chain rule. So we're going to have f prime of g of x times g prime of x in the integrand of an indefinite or definite integral. So for example, if I took the derivative sine of x squared, well, by the chain rule, that would be cosine of x squared times 2x. So now, if I immediately after taking that derivative were to ask you, well, what is the antiderivative of 2x cosine of x squared dx? Well, of course, hopefully, you could tell me that this antiderivative is sine of x squared plus c. Because, of course, we just took the derivative previously and we saw what this answer was, and now this answer is in the integrand. What we want to start to do is develop an eye for looking at an integrand and seeing it as the result of the chain rule. So what we're kind of looking for here, what I want you to notice is that inside of the cosine function, I have x squared, and its derivative is on the outside being multiplied. There's my 2x. So I can sort of see this inside function g of x and its derivative multiplied on the outside. So I want you to keep that in mind as we attempt to apply the substitution method. So the substitution method for indefinite integrals says that if f of x is an antiderivative of f prime of x, then the integral of f prime of u of x times u prime of x dx is equal to f of u of x plus c. So hopefully you can see this is the chain rule in reverse. There's my inside function u of x and its derivative on the outside u prime of x, and the antiderivative is just that an original composition f of u of x, and then we need that constant plus c. So now let's go ahead and look at a strategy for solving integrals using U substitution. Here's a strategy for integrals using U substitution, and it has all of these parts. So instead of just reading them, let's go ahead and take a look at an example together and apply this strategy for using U substitution. In this example, we want to evaluate the integral of x times x squared plus 3 to the 5th dx. Alright, so the strategy starts by saying in the integrand, we want to identify this function u of x. And it's commonly, but not always, an inside function, or the function in the denominator. So when looking for this u of x, you're often also looking to find its derivative or its modified derivative, so we want to be off by maybe just a constant in the integrand somewhere. But that isn't always the case. So again, this is what makes integration a little tougher, is notice it's not like if it's this, always do this. There's words like commonly or but, sometimes it's a little bit different. So this is just going to be a matter of practice in correctly identifying the u for u substitution. So in this particular problem, we are going to let u be x squared plus 3. So this is an inside function. It's inside of x to the 5th, and multiplied on the outside is a modified derivative of this u that we've chosen. So the derivative of x squared is plus 3 is 2x, and on the outside I have this function x. So I'm going to go ahead and let u equal x squared plus 3. And then moving on to step 2, next find du by taking the derivative of u, du dx. So we'll do that first. So du dx, the derivative of u with respect to x, is 2x, and multiplying the dx, the differential, to the other side. So now what we have is that du is 2x dx. All right, and before I actually do my substitution, because the next step is perform a change of variables by replacing the function and its derivative with u and du, what I'm going to do is I'm going to do a little bit of rewriting of the integrand. Since multiplication is commutative, I'm going to switch the places of x squared plus 3 to the 5th and x, so that I can see right now what's about to happen here is this x squared plus 3, right, this inside piece right here, well, I said let's call that u. And now I need to get rid of this x dx right here. So this left-hand side became u to the 5th. Now this right-hand side, x dx, I want to go ahead and replace that with something involving u's. I want to change everything to u's and du's. Well, I know that du is equal to 2x dx. Well, I only have an x dx to replace. So I'm going to go ahead and divide both sides by 2, or multiply both sides by a half. So I know that 1/2 du is equal to x dx. So now I'm going to go ahead and replace this quantity, x dx, with what I know it equals, which is 1/2 du. So 1/2 du. So now I have this integral that's entirely only involves the variable u. So I'm going to go ahead and take the constant to the front, so that 1/2, I can pull constants, numbers, outside of the integral. And here's now what I'm integrating, u to the 5th du. And that's really nice. I can just apply the power rule for integrals there. So I can leave the 1/2 in the front, and then here I would have u to the 6th over 6 plus c. So add a power, divide by the new power. So this is 1 over 12, and it would be u to the 6th, but now instead of u, I want to go ahead and plug my x squared plus 3 back in. So I have x squared plus 3, and all of that is raised to the 6th power plus c. Since the original integral involved the variable x, I want my answer to involve the variable x as an indefinite integral. So all of this over here is like scratch work, and I typically do it underneath the indefinite integral and then show my work, off to the right-hand side just to keep myself organized. All right, now we'll evaluate the integral of x plus 1 times e to the x squared plus 2x plus 1 dx. So for this problem, we're going to go ahead and let our u be x squared plus 2x plus 1. So if I let u be x squared plus 2x plus 1, then its derivative is going to be 2x plus 2. So I'm going to skip the step where I put du dx, because we do have to multiply by the differential. We do want the dx on this side, so I'm just going to jump straight to that, my du, my derivative. And we can see that we are going to want to get rid of the leftover part, the part involving x that we need to get rid of is this x plus 1 and this dx. Well, I have 2x plus 2 dx, so hopefully you can see that here we're going to go ahead and factor out a 2. So we have 2 times x plus 1 dx equals du. So we'll go ahead and divide out that 2, or multiply by 1/2. So 1/2 du is equal to x plus 1 dx. So my new integral is going to become, so I'm going to do things a little quicker this time. So I'm not going to bother rewriting it. Notice I didn't put the x plus 1 over here by the dx, but I want you to notice the x plus 1 and the dx gets replaced by 1/2 du. Well, I'm going to go ahead and keep that 1/2 in the front, and then the du in the back where the differential is, and then the actual integrand will now become e to the u. And that's it. So we got rid of x plus 1 dx by replacing it with the half du. We put the half here, the du here. And then this part became e to the u because x squared plus 2x plus 1 was just u. And from here, we take the antiderivative. Well, on this one, it's kind of nice, right? The integral of e to the u is just e to the u plus c. And then we go ahead and plug u back in. So 1/2 e to the x squared plus 2x plus 1, and then plus c is my answer. And here, I just want to point out, sometimes people see parentheses and they want to let that quantity in the parentheses be u. Well, if you let x plus 1 be u in this problem, then the derivative would be just dx, and we wouldn't have a way to get rid of this, whole x squared plus 2x plus 1 part. We need to change everything into all u's. We wouldn't have a way to get rid of this part. So again, it's just sort of taking the time to do practice and develop that eye for picking the correct u. In this next example, we have to evaluate the integral of tangent x dx. And this doesn't have a general antiderivative. We don't know what we take the derivative of to get out just tangent x. And right now, we just have one function. We just have tangent x. So, what do I pick as my u? If I let u be tangent x, well, the derivative is secant squared x, and I don't see that anywhere. So to start this problem, we actually have to rewrite tangent x as sine x over cosine x dx. And in this example, we're going to go ahead and now let u equal cosine x. And then we can see that when we take its derivative, so du is going to be negative sine x dx. And I do have at least a sine x dx. So what I'm going to have to do is just multiply that negative to the other side. So negative du is sine x dx. So I'm going to be able to replace sine x dx with negative du, and then I'm going to be able to replace cosine x with my u. So my integral will become the integral of negative du over u. I'm going to have negative du over u. Well, I can also just take out that negative. So what I have is du over u, and that integral is the natural log of the absolute value of u plus c. So remember, since this is to the first power, this is the natural log as the antiderivative. And then we're going to go ahead and plug the u back in, which in our example was cosine x. So we have negative the natural log of cosine x plus c. And here, maybe you might be thinking, well, could I have let u be sine x in this case? And the answer is no, that wouldn't work out. So if we let u be sine x, the derivative is cosine x, and we actually don't have cosine x. We have 1 over cosine x, or we have secant x. So that actually would not work out. And one other tip, the differential dx can never be in the denominator. So we just want to make sure nothing weird like that ever happens where the differential dx ends up, or du ends up in the denominator. For this example, we want to evaluate the integral of 3x divided by the square root of x squared minus 1 dx. So here, we're going to go ahead and let u equal x squared minus 1. And if I think about the derivative of this, my du is going to be 2x dx. Now, I have a 3x dx, but I'm only off by a coefficient, so that's fine. So what we're going to go ahead and do, a couple things. So first, I'm only going to want to get rid of an x dx, so I'm going to go ahead and say that, well, 1/2 du is equal to x dx. And then in my original problem, I'm going to go ahead and take the constant out. Remember, I could take a constant out of an integral, and I'm going to think about this as x dx over radical x squared minus 1. So right now, when I make my substitution, hopefully it'll be pretty clear that x dx, that part right there, is going to get replaced with 1/2 du. And actually, I'm going to go ahead and put the 1/2 in the front. Well, that's just putting 3 times 1/2, or 3 halves in the front. And then in the numerator, putting my du. And then we have over the square root of, and now the x squared minus 1 was my u. So now I'm going to go ahead and actually take the antiderivative. So that's another sort of really common mistake in these problems, is not actually taking an antiderivative. So remember, the symbol means find the antiderivative. I have to rewrite this as u to the negative 1/2 du. So I'll keep that constant in the front. And when we take the antiderivative, it's going to be u to the 1/2 when I add 1. And then I would have to divide by 1/2, which is the same as multiplying by the reciprocal, multiplying by 2/1 plus c. So now those 2's would cancel. I get 3, and then u to the 1/2, or the square root of, and my u was x squared minus 1, and then plus c. So this is my indefinite integral. In this example, I want to evaluate the integral of sine of the natural log of x over x dx. So here we're going to go ahead and let u be natural log of x, because the derivative is 1 over x dx, and I can see that is involved in my integrand. So if u is the natural log of x, well then du is 1 over x dx. So now I'm going to go ahead and rewrite my integrand for this one, just to help see it a little bit better, that this is sine of ln x times 1 over x dx. So my integral is going to become sine, and then of u, and then 1 over x dx, well, that's my du. So now I can find the antiderivative of sine u du. So that's going to end up being negative cosine of u plus c. And then I can substitute my u back in. So negative cosine, and we'll go ahead and plug that natural log of x back in. So negative cosine of ln x plus c. In this example, I want to evaluate the integral of x times radical 5x plus 1 dx. So this one's going to work out a little bit different. We're going to go ahead and start it in the similar fashion. We're going to let u be the inside of this square root function. So we're going to let u equal 5x plus 1. All right, well now du, so du is going to be 5 dx. Well, I need to get rid of an x dx. So what I'm going to do right here is I'm going to say, well, 1/5 du is equal to dx. So here's what I have so far. Let's try this. I still have an x, so I'm going to leave it there. I have a square root of u, because I can replace 5x plus 1 with u. And then I can replace dx with 1/5 du. So I can keep that 1/5 in the front and that du in the back. So I have a problem here. I don't have a change of variables. I don't have all variable u. I still have this x here. Well, if I go back to my original u was equal to 5x plus 1. So if we do a little bit of rewriting here, we can solve for x. We can subtract the 1 and divide by 5 so that we end up with x is equal to u minus 1 over 5. So we're going to go ahead and now replace that x with that u minus 1 over 5. So here's what we have overall. I have 1/5 the integral, and I'm going to keep it all in one big set of parentheses, u minus 1 over 5, and then times the square root of u du. So it sort of looks messy, but we can actually evaluate this integral. So this 5 in the denominator, it's like 1/5, so I can pull it to the outside and I'd get 1 over 25. And then I have this binomial u minus 1 times u to the 1/2 du. Now here, the 1 over 25 stays in front. Now I can't take the antiderivative of each piece separately. I do have to distribute in this u to the 1/2. So it will be u to the 3/2 minus u to the 1/2 du. And I know you're thinking, we're not even done yet, because we're not. We still have to take the antiderivative. So 1 over 25 is going to stay in front, and I'm going to keep parentheses here. I'm going to have u to the 5/2, so I add a power, and then times the reciprocal times 2/5. And then here I have minus u to the 3/2 times 2/3. And then we're going to have our constant c in the back. All right, so now this is the antiderivative of this function here with u's, so we just have to go ahead and plug the u back in, and we'll also distribute the 1 over 25 back in. So we're going to end up here with, let's see, 2 over 125, and I'll leave a space to plug that u back in, to the 5/2, and then minus 2 over 75, leave a space to the 3/2, plus c. And that space is for my original u, my 5x plus 1. So this whole thing is my answer. So this is still a u substitution, it just has a little bit of a twist on it. We had to solve my original u in terms of x, or so that we could solve for x to replace it and make everything in terms of u. Here I want to evaluate the integral of dx over tan inverse of x squared times 1 plus x squared. So it might be a little bit easier to think about this as 1 over tan inverse of x squared times 1 over 1 plus x squared dx. So maybe this will help us try to identify what our u should be. So when I see this 1 over 1 plus x squared, I should immediately be thinking that's the derivative of tan inverse of x. And tan inverse of x is sort of inside this x squared function, so that's what I want to let be my u. I want u to be tan inverse of x, so that du is 1 over 1 plus x squared dx. And then my substitution will work out pretty nice. I'm going to have 1 over, we're going to have u squared, so there's my u, and then this whole piece right here is just du. So it turned it into a nice little integral. So 1 over u squared du, which is, oops, the integral of u to the negative 2 du, or u to the negative 1 over negative 1 plus c. So we can't forget to actually take the antiderivative. Real quick, it's not natural log of the absolute value of u squared. Remember, we have to rewrite it and use the power rule. So what it is negative 1 over, and then we'd be dropping that tan inverse to the bottom, right? Tan inverse of x plus c. And this is a good time to mention that we can't like bring this to the top and make it tan x, like as if this was a power, right? This is just the notation for inverse, like arctangent. So we can't move it to the top and like make it tangent. And sometimes people want to do that. So this is my answer. In this one, we want to evaluate the integral of x cubed times the square root of x squared plus 5. Now, if we go ahead and let our u be this sort of inside function, so u equals x squared plus 5, we'll see what happens. If we take the derivative, du, we're going to end up with 2x dx. All right, well, I have x cubed dx, so let's just go ahead and divide by that too. So 1/2 du equals x dx. So right now I'd be able to replace x squared plus 5 with u and replace this x, one of these x's, there's 3 copies here, the x dx with a 1/2 du, but I'm still going to have an x squared left over. So let's kind of maybe split this up to be able to see that. So I'm going to put the radical x squared plus 5 in the front. And I can think about that x squared or x cubed as x times x squared dx. So now what I have as of right now is the integral of the square root of u, and then I can replace the x and the dx with a 1/2 du, so I can put the 1/2 right there in front. I could put the du in back, but nothing right now replaces my x squared. However, we can solve the original u for x squared. So x squared is equal to u minus 5. So it should feel pretty familiar. It's just a little twist on a problem we did earlier. So if I replace x squared with u minus 5, now I will be able to distribute and then take the antiderivative. So we would have to distribute first this radical u to both pieces. So we'll leave the 1/2 in front. We'll have u to the 3/2 minus 5u to the 1/2 du. And we can take the antiderivative of each piece. Keep that 1/2 in front. It does apply to both terms. So we have u to the 5/2 times 2/5 minus here, we'll leave the 5 in front, we have 5 to the 3/2 times 2/3 plus c. And then we're going to just go ahead and multiply the 1/2 in and plug our u back in. So if we multiply the 1/2 times 2/5, we get 1/5 u to the 5/2. So leave a space for that u. And if we distribute in the 1/2 over here, we'll end up with negative 5/3 u to the 3/2 plus c. And plugging that u back in, we get x squared plus 5 as our original u. So here is my general antiderivative. Here we want to evaluate the integral of 1 over e to the x plus e to the negative x. And I'll realize quickly that I'm stuck. If I let u be the entire denominator, the derivative will be e to the x minus e to the negative x, and that's not involved anywhere. So what I want to start by doing here is a little bit of algebra first. So what I have is 1 over e to the x plus 1 over e to the x. So I'm rewriting that e to the negative x as its own little fraction, 1 over e to the x dx. And then I created a complex fraction, which I can get rid of by clearing fractions, multiplying the top and bottom by e to the x. So I'd get e to the x over, here if I multiply the denominator, both pieces, by e to the x, I'll get e to the 2x plus 1 dx. And so now this gives me a little more to work with. If I think about letting u be the entire denominator here, though, I'm going to get stuck again. If I take the derivative of the denominator, I'm going to get 2e to the 2x, and I only have an e to the x on the top. So there's one additional little piece that we have to recognize, and this will come with practice. This one is a tough one to see. So e to the 2x, that's e to the x quantity squared. So what am I going to let be u here? My u is going to be e to the x, and the one I'm talking about is this one right here. That's what I'm going to let be my u. Because then du, its derivative, is e to the x dx, which is in this numerator right here, e to the x dx. So what this problem is going to become is, I'm going to move it back over here, next line, it's going to become the integral of du over, I replace e to the x with u, so that's going to be u squared plus 1. And this has an antiderivative that we know. It is tan inverse, or arctangent. So let's use arctangent of u plus c. And then u was, of course, e to the x, so my answer here is arctangent of e to the x plus c. So that one involved a little bit of algebra, was a little bit tricky, and it comes with practice. So we've done a variety of problems, and you've seen different strategies, but it's only going to get better with practice. The substitution method, or U substitution, for definite integrals. The substitution method for definite integrals says that if u of x is differentiable on ab, which is the limits of integration for our integral, and f of x is integrable on the range of u of x, then our integral from x equals a to x equals b of f of u of x times u prime of x dx sounds complicated, but this just means our substitution, as we did with indefinite integrals, our substitution is going to be the same as the integral of u of a to u of b of f of u du. So we're going to have to change the x equals a and x equals b limits of integration into u's to match the variable that we have substituted in now. So we're going to have to address the fact that the limits of integration were x values, but now we're turning everything else into u's, so we also have to turn those limits of integration into u's as well. So let's take a look at some examples. Alright, let's evaluate the integral from 0 to 2 of x squared times the square root of x cubed plus 1 dx. So when I have the differential dx, that implies that the limits of integration are also x values. So I'm going to go ahead and sneak in a little x equals here to just remind myself that those are currently x values. Now let's proceed with starting our u substitution. The u that we're going to pick is inside the square root. We're going to pick x cubed plus 1 as our u. And then we're going to find the derivative of that with respect to x. So du dx is 3x squared. So du is 3x squared dx. I'm only looking to replace x squared dx. So I'm going to divide both sides by 3 or multiply by a third. So 1/3 du is equal to x squared dx. So what's going on now with my integrand is that x squared dx, so the x squared and the dx part, is going to get replaced with 1/3 du. And I'm going to go ahead and keep that 1/3 in the front. So let me move this over. Oops. So I'm going to have 1/3. And I'm going to put the du in the back. So the 1/3 du replace x squared dx, and then x cubed plus 1 gets replaced with u. So x cubed plus 1 is going to be replaced with u, so my integral is going to be the square root of just u. So I've changed my integrand and my differential to the variable u, but my limits of integration are still x values right now. So it wouldn't be accurate to put right now 0 to 2 without labels, because if you just put 0 and 2, now you're implying that these are u values, but they're not. They're still x values. But we can fix that. We can turn them into u's using our substitution equation. U is equal to x cubed plus 1. So u of 0
is 0 cubed plus 1. So I turned this x value into a u value. I plugged x equals 0 into x, and that makes it a u value. So now this would be a 1, and then u of 2, plugging in 2 for x, I did 2 cubed plus 1, which is 9. So now I've made my limits of integration into u values. So I don't technically need to write u equals 1 and u equals 9 because it's already implied that they're u's because of the differential. And so now sort of the benefit of doing that, of changing them into u's, is that I actually don't have to care about this information at all anymore. Now, this is just like its own fundamental theorem of calculus problem. I can simply find the antiderivative of the square root of u, and then plug in 9 and plug in 1 and subtract them, and that's my answer. So in other words, this would be, so remember, square root of u is u to the 1/2. So this would be 1/3, and then we'd have u to the 3/2 times 2/3. So I added a 1 to 1/2, and then instead of dividing by 3/2, multiply by the reciprocal, and then this is going to be evaluated from 1 to 9, because my answer is a number. So it's going to be 2/9, and then 9 to the 3/2 minus 2/9, 1 to the 3/2. So plug in 9 and then plug in 1, subtract them, just using the fundamental theorem of calculus. And then I'm just going to evaluate this to get my numerical answer. So 9 to the 3/2, that's the square root of 9, which is 3. 3 cubed is 27. So 2/9 times 27 minus just 2/9. So we have 54/9 minus 2/9. So we get 52 over 9. So we knew our answer was going to be a number because this was a definite integral with numbers as my limits of integration. We used u substitution, but because we changed the integrand and the differential to u's, we also went ahead and turned our limits of integration into u's, which just turned it into a completely, different problem to evaluate with the fundamental theorem of calculus, and we didn't have to go back at all to the x variable. We just proceeded forward to get our numerical answer. Let's look at another example. I have evaluate the integral from 0 to pi over 2 of cosine cubed x times sine x dx. So once again, just to remind ourselves, these are x values as my limits of integration. I'm going to do u substitution here, letting u be cosine x, and that's because that's like my inside function. Cosine x is inside of x cubed, and a version of the derivative of cosine is multiplied on the outside. So the derivative of cosine is negative sine. So we have du is negative sine x dx. I ultimately just want to replace sine x dx, so I'm going to replace that with negative du. Negative du is sine x dx. Okay, so let's go ahead and move forward here. This is going to become negative the integral. So I'm replacing the sine x dx, right, with negative du. So I'm going to put the negative in the front and the du in the back. And then cosine gets replaced with u, so this integral is simply u cubed. And then I have my limits of integration to handle or to deal with. Now, it is definitely an option, and it's the one I recommend, to turn these into u values. So to plug in x equals 0 into cosine to make it a u value, and then plug pi over 2 into cosine to make it a u value. But I just want to show in this example how you can, if you want, leave them as x values, but then you do have to put the original cosine x function back in. So I just want to provide you with this option and talk about some additional steps you have to include to make sure that what you're writing down is accurate. If you want to leave these as x values, you have to write x equals. So you'd have to put this integral goes from x equals 0 to x equals pi over 2. So as I said before, if you just put 0 to pi over 2 still, you're implying that those are u values. So this would be an incorrect equal sign usage, and we don't just ignore equal signs, we have to use them and use them correctly. So if you want to leave these as 0 and pi over 2, then you have to label them as x values. So now what we do is we would find the antiderivative of u to the third, which is 1/4. So we'd have 1/4 u to the fourth. And then this is, I'll put a negative there too. This is evaluated again from x equals 0 to x equals pi over 2. And why it's so helpful to leave it as x values as well is because then you're not tempted to make the mistake right now of plugging pi over 2 into u and plugging 0 into u, because these are not u values. So what you would do then is put u back in, just like when your indefinite integrals were done. So you would do negative 1/4 and then cosine to the fourth of x. And then this is evaluated from 0 to pi over 2. And now you can stop writing x equals because you put x back in. So all the variables and limits here match. And then you'd plug in pi over 2 and then you'd plug in 0. So you'd get negative 1/4. And then we'd have cosine of pi over 2 to the fourth minus negative 1/4 cosine of 0 to the fourth. And let's see, cosine of pi over 2 is 0. So this whole first term here is 0. Minus negative 1/4 is plus 1/4. And cosine of 0 is 1. So 1/4 times 1 to the fourth, that just gives us 1/4 as our answer. So I can tell you, I personally use and recommend using the method of changing everything to u's and then just not going back to x's at all. Because I see more students make mistakes when they try to leave the limits of integration as x, because they forget that they left them as x's and then they just plug those x's into the variable u, which would give you a completely different and incorrect answer. So I recommend changing everything, including the limits, to u's, but it is possible you will still get the right answer if you leave them as x's, indicate that they are x's, and then go back and turn your u variable into the x function that you replaced it with before plugging in those limits of integration.